The sun you think you know isn't the sun that truly exists. The real sun is stranger, a star that sings without sound, storms without warning, vibrates like a living creature, and bends space itself in ways we still don't understand. It looks calm from Earth, but only because distance hides its true behavior, a behavior so wild that even a single flare can reach us faster than thought. Tonight, we uncover all of this gently, because in this video, we will know about 100 lesser-known facts about the sun that will help you sleep listening to it. The sun contains 99.86% of all the mass in the entire solar system. When you think about everything that exists around us, the planets, their moons, the countless asteroids, the drifting comets, even the dust floating quietly between worlds, all of it together still makes up less than 1% of the material in our solar neighborhood. Almost everything is inside the sun. Its gravity holds every planet in place, guiding them like small dancers circling a massive glowing partner. The sun isn't just the center of our solar system, it is the solar system. You could fit about 1.3 million Earths inside the sun. It's hard to imagine a number that big, but picture this. If Earth were a tiny marble, then the sun would be a giant sphere so enormous you'd need more than 1 million marbles to fill it. When we look at the sun from Earth, it feels small because distance shrinks its appearance, but up close, the sun would tower over our world like a blazing, godlike titan of light. A small chunk of the sun's core, the size of a sugar cube, would weigh over 150 tons on Earth. At the sun's center, matter is squeezed under unimaginable pressure. Hydrogen atoms are pushed so tightly together that a tiny bit of the core would be heavier than a fully loaded airplane if somehow placed on Earth. This crushing pressure is what allows nuclear fusion to happen, the process that keeps the sun shining, making life possible on our planet. Light created in the sun's core takes between 100,000 and 1 million years to escape. Deep inside, photons constantly slam into particles, bouncing around in every direction like someone lost in a maze of glowing walls. They move only inches at a time before being scattered again. For hundreds of thousands of years, they struggle to rise through the dense layers of the star before finally reaching the surface. But once sunlight reaches the surface, it only takes 8 minutes and 20 seconds to reach Earth. After spending ages trapped inside the sun, a photon suddenly becomes incredibly fast once it breaks free. It races through the emptiness of space at the speed of light, crossing nearly 93 million miles in just a few minutes. The light touching your skin right now began its journey long before humans existed. The sun is actually white, not yellow. From space, the sun shines with a pure, brilliant white light, a perfect blend of every color you can imagine. It looks yellow to us only because our atmosphere scatters shorter wavelengths like blue and violet, leaving behind the warm colors that reach our eyes more directly. Sunlight appears yellow on Earth because our atmosphere scatters blue light. As sunlight enters the sky, tiny particles in the air scatter the blue part of the spectrum in all directions, creating the blue sky we see each day. The remaining colors pass through more clearly, giving the sun its familiar golden glow. But remove the atmosphere, and the sun becomes dazzlingly white again. The sun produces continuous sound waves deep inside itself, but space is silent. Inside the sun, powerful pressure waves ripple through the plasma, creating vibrations like a massive rumbling musical instrument. These waves travel through the sun's interior, shaping its structure. But space has no air, no medium for sound to travel through, so even though the sun is constantly singing, we will never hear it directly. The equator of the sun retorts faster at its equator than at its poles. Because the sun is not a solid object, different parts of it spin at different speeds. The equator completes one rotation in about 24 days, while the poles take around 35 days. This uneven spinning twists the sun's magnetic field like a giant rubber band, creating storms, sunspots, and eruptions that can ripple through the solar system. The sun's core reaches about 27 million degrees Fahrenheit, 15 million degrees Celsius. At this temperature, matter behaves in ways that barely make sense on Earth. Atoms move so quickly and collide so fiercely that they fuse together, releasing vast amounts of energy. This fusion reaction is the heartbeat of the sun, generating the light, heat, and warmth that make life possible on our planet. The equator of the sun spins once in 24 days, but the poles spin once in 35 days. The sun is not a solid body, it is a giant sphere of hot, flowing plasma, so different parts of it spin at different speeds. Near the equator, the sun spins quickly, almost like a dancer turning with graceful confidence. But near the poles, the rotation slows, like that same dancer easing into a calm, steady glide. This uneven rotation stretches and twists the sun's magnetic field over time, creating patterns and tensions that will ultimately burst into the storms we see on its surface. The sun loses about 4 million tons of mass every second as energy. Every moment you're alive, every blink, every breath, the sun is sacrificing enormous amounts of itself to shine. Through nuclear fusion, mass is turned into pure energy, and that energy streams outward in the form of light and heat. 4 million tons vanish every second, yet the sun is so massive that it can continue this endless giving for billions of years without weakening. If the sun stopped shining this instant, you wouldn't know for 8 minutes. We see the sun not as it is right now, but as it was 8 minutes ago. That is the time it takes for light to make the long journey across space. If the sun suddenly disappeared, a frightening thought, the darkness would reach us only after those silent 8 minutes had passed. Until then, everything would look calm, unchanged, as if the universe were holding its breath before the truth arrived. The sun emits every color of light, even those we cannot see. Our eyes catch only a small portion of the rainbow hidden in sunlight. Beyond the reds and violets lies a world of ultraviolet, infrared, X-rays, and even radio waves, all pouring out from the sun in a constant stream. We live bathed in this invisible light every day, unaware of the glowing spectrum around us that is too wide, too rich, too powerful for our senses to grasp. The sun's magnetic field is constantly shifting and breathing with time. Magnetism flows through the sun the way winds move through Earth's skies, swirling, curling, building into storms, then calming again. This magnetic field twists and coils as the sun rotates at uneven speeds, storing energy like a giant spring slowly tightening. When the tension becomes too much, the sun unleashes bursts of plasma and light that travel across the solar system. The sun experiences an 11-year cycle of activity, growing calm and then stormy. Every 11 years, the sun enters a new phase, moving from quiet periods with few sunspots into more violent years filled with solar storms and eruptions. These cycles affect Earth in subtle ways, influencing auroras, radio signals, and even the environment in the upper atmosphere. It is as if the sun has a slow, cosmic heartbeat pulsing with the rhythm of time. During active years, sunspots can grow larger than the planet Jupiter. A sunspot may look like a dark smudge on the surface of the sun, but this smudge can be so massive it could easily swallow entire planets. These darker areas are slightly cooler regions where magnetic fields knot together. They appear small from far away, but in truth they are enormous islands floating in a sea of fire. Some solar flares release more energy than millions of nuclear bombs. When the sun's magnetic fields snap and reconnect, they unleash flares so powerful that even from 93 million miles away, their effects can reach Earth. These explosions send waves of radiation into space, carrying more energy in a single moment than humanity has produced throughout its entire history. Sometimes the sun ejects huge clouds of charged particles called coronal mass ejections. These eruptions launch billions of tons of solar material into space, forming clouds that expand like glowing storms. When they head toward Earth, they can shake our magnetic field, create magnificent auroras, and even disrupt electricity on the ground. Thankfully, most of them drift harmlessly into the emptiness of space. The sun's magnetic poles flip every 11 years. North becomes south, and south becomes north. This quiet, powerful reversal is part of the sun's natural cycle. The magnetic field slowly weakens, reorganizes itself, and then returns flipped. To us on Earth, this change passes unnoticed. The sun looks the same, rises the same, warms us the same. But inside the sun, an entire magnetic world rearranges itself as naturally as the changing of seasons. Coronal mass ejections can launch billions of tons of plasma into space. These eruptions are like the sun exhaling with unimaginable force. A single CME can contain more material than all the oceans on Earth combined, heated to millions of degrees and hurled outward faster than any wind on our planet. From far away, they look like vast glowing clouds rising from the sun's surface. But if one were directed toward Earth, it could disturb our magnetic field, brighten our skies with auroras, and even create ripples that touch our technology. Despite their power, most CMEs drift into empty space, fading quietly like sparks from a distant fire. A powerful solar storm can travel at millions of kilometers per hour. These solar storms accelerate so rapidly that they can cross the space between the sun and Earth in as little as 17 hours. Imagine a wave of electrified gas racing faster than anything built by humans, crossing 93 million miles in less than a day. The speed of these storms reminds us how small and slow our world is compared to the forces that shape our solar system. In 1859, a massive solar storm, the Carrington event, caused telegraphiers to spark and catch fire. Long before smartphones and satellites, people relied on telegraphiers to send messages across continents. During this storm, the wires carried so much electricity from the sun that sparks flew from equipment, operators received shocks, and some telegraph machines even worked without being plugged in. It was the first time humanity understood that the sun could reach across space and touch our technology. A similar solar storm today could damage power grids and satellites. Modern life depends on delicate systems, GPS, communication satellites, electrical networks. A massive solar storm could overload circuits, confuse navigation systems, and cause blackouts. Scientists carefully monitor the sun every day, watching for eruptions that could affect the world. Luckily, Earth's magnetic field protects us from the worst of these events, absorbing much of the sun's wild energy before it reaches the surface. The sun's magnetic field stretches far beyond Pluto. This enormous bubble of magnetic influence is called the heliosphere. It's like the sun's invisible breath, pushing outward in every direction and filling the solar system. Inside this bubble, the sun shapes the movement of charged particles and protects the planets from harmful radiation drifting through the galaxy. The heliosphere is our shield, created not by walls or metal, but by the steady pulse of a distant star. The solar wind shapes the tails of comets, making them always point away from the sun. No matter where a comet travels, its glowing tail is pushed outward by particles from the sun. This means a comet's tail doesn't trail behind it like smoke. It streams away from the sun like a shimmering banner of ice and dust. The tail always faces the same direction relative to the sun, a quiet reminder that comets are at the mercy of a star's breath. The sun vibrates like a giant musical instrument. Deep inside, sound waves bounce and ripple through the sun's layers, passing energy across thousands of kilometers. These patterns scientists study to understand what lies beneath the surface. Though we can't hear it, the sun is always humming, a constant rolling song shaped by fire and gravity. It is a melody we translate through instruments, revealing a star alive with motion. Solar storms can create auroras visible much farther south than usual. During strong storms, the colorful lights usually seen near the poles can spread into regions that rarely experience them. Greens, pinks, and purples ripple across the sky, painting the night in soft, shifting curtains of light. These auroras are the result of solar particles dancing with Earth's magnetic field, a cosmic performance that begins on the surface of the sun. Sunspots look dark, but they are extremely hot, hotter than lava. A sunspot appears dark only because it is slightly cooler than the surrounding areas. In reality, sunspots are still thousands of degrees hot, so hot that anything known on Earth would vaporize instantly. They look like shadows on the sun's surface, but they are swirling, turbulent regions where magnetic fields twist tightly together. Some sunspots have magnetic fields thousands of times stronger than Earth's. These regions are so magnetically intense that they can hold back the boiling plasma beneath them, slowing its movement and creating cooler patches. The magnetic fields there are so strong that if a sunspot were somehow placed on Earth, it would rip apart compasses, electronics, and anything sensitive to magnetic force. On the sun, these magnetic knots are simply part of its ever-changing surface. The sun's magnetic field forms a giant protective bubble around the solar system called the heliosphere. This invisible bubble stretches billions of miles into space, far beyond the orbit of the outer planets. Inside this bubble, the sun's magnetic field and solar wind push back harmful particles drifting through the galaxy. Every planet, including Earth, lives inside this protective shield. Without the heliosphere, high-energy cosmic rays would bombard our world constantly. But because the sun is always breathing outward, filling space with its magnetic influence, it creates a safe nest where our solar system can exist in relative peace. The solar wind constantly flows outward and shapes everything around it. Think of the solar wind as a soft but steady river of tiny charged particles. This flow never stops. It moves through space day and night, pushing against planetary atmospheres, brushing past moons, and sculpting the long, glowing tails of comets. It stretches far into the dark until it weakens to nothing at the very edge of the heliosphere, where the influence of the sun finally fades. Beyond that point lies true interstellar space, untouched by our star. Comet tails always point away from the sun, no matter which direction the comet is traveling. It doesn't matter if a comet is moving toward the sun, away from it, or sideways. Its tail still streams in the opposite direction from the sun. This happens because the solar wind pushes dust and gas outward like a breeze blowing on a dandelion. From Earth, the glowing tails look like they're trailing behind, but in space, direction works differently. The sun is the ruler of motion, and its wind decides where a comet's tail must point. The sun sends out waves that vibrate through its entire body like ripples moving through a drum. These waves are caused by rising and falling currents of hot plasma deep inside the sun. They shake the sun from the inside, producing movements that travel upward through its layers. Scientists study these vibrations to understand what the sun looks like beneath its surface because we can't see into the sun directly. It's almost like using sound to map the inside of a musical instrument, except the instrument is a star. Some auroras on Earth are directly caused by powerful solar storms. When large amounts of solar particles reach Earth, they follow our magnetic field down toward the poles. There, they collide with particles in our atmosphere, creating glowing lights that shimmer and dance across the sky. During major solar storms, these lights can appear much farther from the poles than usual, painting unexpected places with curtains of green and purple light. It's as if the sun is tracing shapes in our sky from millions of miles away. Solar flares are so powerful that they can affect radio signals and GPS systems on Earth. A flare is a burst of energy released when magnetic fields near the sun's surface snap and reconnect. The radiation that follows can cause temporary disturbances in the upper atmosphere, making it harder for radio waves to travel. Pilots, sailors, and even satellites sometimes feel the effects. For a few minutes or hours, the sun quietly reminds us that it has the strength to touch our technology from across nearly 100 million miles of space. A solar flare can accelerate particles to nearly the speed of light. In a flare's violent explosion, particles get whipped into motion with incredible force. Some move so fast that they reach Earth just minutes after the flare occurs. These particles are powerful enough to penetrate satellites, damage delicate electronics, and even pose risks to astronauts outside Earth's protective atmosphere. Yet on the surface of Earth, we barely notice them. The planet's magnetic shield absorbs the danger way before it reaches us. Solar tsunamis, giant shock waves, can race across the sun's surface. These tsunamis are not made of water, but of hot plasma moving across the sun at hundreds of miles per second. Imagine a wave taller than Earth itself rolling across a sea of fire. Scientists first saw one in 1997, watching in awe as a massive ripple spread outward from a solar flare, like someone tapping the surface of a glowing liquid. The surface of the sun is covered in flowing rivers of plasma thousands of miles deep. Even though the sun looks smooth from far away, up close it is boiling and swirling constantly. Huge currents rise and fall as hot plasma pushes upward and cooler plasma sinks. These cells form giant cells, some the size of continents, that bubble like water heated in a pot, except instead of water, it's electrically charged gas heated to thousands of degrees. The sun's magnetic field creates patterns and currents deep inside the star. Some of these currents act like conveyor belts, slowly dragging magnetic energy around the sun over many years. Others twist and flip directions, shifting with the sun's 11-year cycle. These internal motions are invisible to our eyes, but they control everything we see: sunspots, flares, storms, and the shimmering corona during an eclipse. It's almost like the sun has a hidden heartbeat driving the rhythm of its entire existence. Humans have been studying the sun for at least 5,000 years. Before telescopes or satellites, ancient civilizations watched the sun with a mixture of fear, respect, and curiosity. They tracked its path across the sky, marked the changing seasons, and built monuments that lined up perfectly with sunrise or sunset on special days of the year. To them, the sun wasn't just a star, it was a teacher, a guide, and a force they didn't fully understand but deeply depended on. For thousands of years, humans have lifted their eyes to the same glowing circle, trying to understand the power that gives life to everything on Earth. The Sun is a G-type main sequence star, a rare class in our galaxy. Even though the Sun feels ordinary to us, stars like it are surprisingly uncommon. Only a small percentage of stars in the Milky Way are similar in size, temperature, and brightness. Many stars are red dwarfs, tiny, dim, and cool. Others are massive blue giants that burn too quickly to support stable planetary systems. But our sun sits in a perfect middle ground, stable and calm enough to nurture life for billions of years. The sun is brighter than about 90% of the stars in the Milky Way. Most stars are faint and small, barely giving off enough light to be seen from afar. If you placed our sun in another part of the galaxy, many distant observers would see it as unusually bright, a standout among dim cosmic neighbors. Its brilliance is not a coincidence, but a gift of nature, enough energy to warm Earth, shape our atmosphere, and support every form of life we know. The Sun orbits the center of the Milky Way once every 230 million years. As we sit here on Earth, it feels like the Sun is standing still, but in reality, the entire solar system is flying through space, moving in a giant orbit around the galaxy's core. One full orbit, one galactic year, lasts about 230 million Earth years. The last time the Sun completed a full lap around the galaxy, dinosaurs had not yet appeared on Earth. In this moment, you, me, and everything we know are riding the Sun, like passengers on a starship drifting through a vast cosmic ocean. Since Earth formed, the Sun has completed only about 20 of these galactic orbits. It's astonishing to realize how young our solar system is when measured against the age of the galaxy. Earth has existed for 4.5 billion years, yet that time represents only a small number of the Sun's journeys around the Milky Way. Each orbit carries our solar system through new regions of space, past star clusters, gas clouds, and cosmic dust, all while life quietly evolves on the tiny blue planet moving with it. One day, the Sun will grow into a massive red giant star. This transformation lies billions of years in the future, but its certainty is written into the laws of physics. When the Sun runs low on hydrogen fuel, its core will contract, while its outer layers expand outward into a gigantic glowing sphere that could stretch all the way to Earth's current orbit. The Sun will turn red, enormous and much cooler on the outside, a completely different star than the one we know today. It will be a breathtaking sight, but one humanity will never witness from Earth's surface. As a red giant, the Sun may swallow Mercury, Venus, and possibly Earth. When the Sun expands, its outer layers will engulf the inner two planets immediately. Whether Earth survives depends on many factors, including how much mass the Sun loses before it grows. It is possible that our planet will be pulled into the Sun's fiery atmosphere. But even if Earth isn't swallowed, it will become far too hot to support water, air, or life long before the Sun reaches its final size. After the red giant phase, the Sun will shrink into a white dwarf the size of Earth. Even though the Sun's outer layers will be blown away into space, its core will collapse into a white dwarf, a small, incredibly dense object glowing with leftover heat. Imagine a star with the mass of the Sun compressed into something no larger than the planet we stand on. That final form will shine softly for trillions of years, slowly fading but never collapsing further. It will be the Sun's last breath of light. White dwarfs can remain hot for longer than the current age of the universe. Even after billions of years of cooling, white dwarfs hold on to heat with incredible stubbornness. Their glow fades extremely slowly, allowing them to shine long after their parent star has died. One day, the Sun will be one of these quiet cosmic embers, a reminder of a star that once nourished planets, oceans, forests, and life. The sun contains traces of every element in the periodic table. We often imagine the sun as pure hydrogen and helium, but hidden within it are tiny amounts of many other elements: oxygen, carbon, neon, iron, and more. These elements came from older stars that exploded long before the sun formed. When those ancient giants died, they scattered their contents across space, creating the cosmic cloud that eventually collapsed to form our sun. In a way, the sun carries the echoes of stars that lived and died before our solar system even existed. The sun contains traces of every element in the entire periodic table. Even though hydrogen and helium make up almost all of it, the sun still carries tiny fingerprints of every element known to science: oxygen, carbon, nitrogen, iron, even elements heavier than gold. These traces came from older stars that lived and died long before our sun was born. When those ancient giants exploded, they scattered rich materials into space. Slowly, over millions of years, all those pieces drifted together and helped form the cloud that collapsed into our sun. So, when we study the sun, we are studying the ashes of stars that existed billions of years before us. Our sun is a second-generation star, not the first in its region of space. This means the sun is part of a cosmic family tree. Older stars lived before it, produced heavier elements through nuclear fusion, and then died in spectacular explosions. Those explosions provided the material needed for planets like Earth to form. So, the iron in your blood, the calcium in your bones, and the oxygen you breathe were all created inside stars long before the sun came into existence. In a way, starlight is not just above us, it's inside us. Scientists can study the sun's interior using a method called helioseismology. They listen to the vibrations rippling through the sun's layers, small waves caused by rising and falling plasma. These waves travel differently depending on what lies inside. By measuring them, scientists create maps of the sun's internal structure, the way doctors use ultrasound to scan inside the human body. It's one of the few ways we can understand what happens beneath the surface of a star we can never visit. The sun contains streams of plasma that rotate faster than the rest of the star. These streams are like underground oceans, flowing thousands of miles beneath the visible surface. They move faster than the layers around them, carrying heat and magnetic energy in long, deep currents. If you could watch them directly, you would see swirling rivers of glowing gas twisting and looping endlessly inside the sun, a restless heart beating beneath the surface. The sun has a magnetic conveyor belt moving energy around the star. This conveyor belt drags magnetic fields across the sun in slow, giant loops. One cycle takes many years, and it plays a major role in the sun's 11-year activity rhythm. When the conveyor belt slows, sunspot numbers decrease. When it speeds up, the sun becomes more active. It's like a hidden engine guiding the sun's long-term behavior, silently controlling when storms form and when the surface remains calm. One of the first recorded solar eclipses happened in 2137 BC in ancient China. More than 4,000 years ago, people were already watching the sky and documenting the strange moment when the sun disappeared during the day. Ancient astronomers studied these events carefully because eclipses often affected rulers, farmers, and religious leaders. Even with no modern tools, early civilizations treated the sun with deep respect, understanding that it was the source of light, warmth, and life itself. Sundials were humanity's first clocks, all based on the sun's shadow. Long before mechanical clocks existed, people measured time by watching shadows move across stone markers. The sun traced a predictable pattern in the sky, and from that pattern, humans learned to schedule their days, harvest their crops, and organize their lives. Every modern clock on Earth can trace its origins back to the sun's steady motion across the sky. The sun helped early explorers navigate the oceans. By studying the sun's position, sailors could determine direction and latitude, guiding them safely across vast oceans. Before GPS, before maps were accurate, before compasses were perfected, the sun was the traveler's most faithful guide. It silently connected continents long before ships could cross them. NASA's Parker Solar Probe is the closest man-made object ever sent to the sun. It travels so close that it actually flies through the sun's outer atmosphere, the corona, a region hotter than the sun's surface. The spacecraft endures temperatures that would melt any normal material, protected by a special heat shield that keeps its instruments safe. It brings us data about the sun that no human-made object has ever touched before, letting us glimpse the behavior of our star from inside its outer layers. The sun produces energy by fusing hydrogen into helium deep inside its core. Every second, deep in the sun's heart, countless hydrogen atoms are forced together under unbelievable pressure. When they fuse, they create helium, and in that tiny moment of fusion, a small amount of mass transforms into energy. This transformation is so powerful that it is the engine that keeps the sun glowing. It's a quiet miracle repeating itself trillions of times per second, creating the light that nourishes our planet, grows our forests, and warms our oceans. Every second, the sun fuses about 600 million tons of hydrogen. Imagine mountains of hydrogen disappearing into bright, blinding energy in the time it takes you to blink. That is what the sun does continuously. Every heartbeat of the universe, it turns unimaginable amounts of matter into glowing, radiant power. Even though it burns through millions of tons of fuel each second, the sun has enough to shine steadily for billions of years to come. Fusion creates particles called neutrinos, which pass through everything, including you. Neutrinos are ghost-like particles born in the sun's core. They move almost at the speed of light, slipping through planets, buildings, oceans, and even your body as though everything were transparent. Billions pass through you every second without you ever noticing. They are silent messengers from the sun's interior, the one place we can never directly reach, carrying information from the heart of a star to every corner of the solar system. It takes sunlight over 30,000 years to reach the surface, but only 8 minutes to reach Earth. A photon born in the sun's core spends thousands of years bouncing, scattering, and struggling upward like a traveler lost in a maze. But the moment it escapes the surface, everything changes. Its journey becomes straight, clean, and fast, racing through space to Earth in just a few minutes. When sunlight touches your skin, you are feeling the final chapter of a journey that began long before human history. The sun emits more energy every second than all humans have used in their entire history. Every burst of sunlight carries far more power than our cities, our machines, and our inventions could ever produce. Even if you added up every watt of electricity, every spark of fire, every engine, every battery ever built, it would not come close to matching a single second of the sun's energy output. Our star is a giant, tireless generator, shining with a strength beyond anything human-made. The sun's magnetic field is carried across the solar system by the solar wind. As the solar wind flows outward, it drags the sun's magnetic field along with it, stretching it into giant spiraling patterns that swirl around every planet. This flowing field shapes the space around Earth, influences our auroras, and even affects the paths of spacecraft traveling through deep space. It is a magnetic breath that fills the entire solar neighborhood. Light from the sun can actually push objects. It exerts radiation pressure. Sunlight may seem gentle, but when it hits objects in space, it can push them with tiny but real force. Over long periods of time, this pressure can alter the paths of dust grains, spacecraft, and even asteroids. Solar sails, thin sheets of reflective material, use this pressure to travel through space without fuel, riding beams of sunlight like silent ships drifting on a cosmic ocean. The sun loses about 1.5 trillion tons of mass every year because of radiation. As the sun shines, it gradually sheds its mass, not visibly, but through the light and particles it emits. Even though 1 trillion tons sounds enormous compared to the sun's total mass, it is tiny. This slow loss will continue for billions of years, a gentle fading that will eventually cause the sun to grow bigger and brighter as it ages. The photons that reach Earth started as gamma rays deep inside the core. When they first formed, the sun's photons were not the soft, warm light we see. They were intense gamma rays, the highest energy form of light. But as they fought their way outward through turbulent plasma and countless collisions, they gradually lost energy, stretching into visible light. By the time they touch Earth, they have transformed into the gentle sunlight that brightens our days and warms our world. Fusion keeps the sun balanced by pushing outward against gravity. Gravity tries to squeeze the sun inward, pulling every atom toward its center with immense force. Fusion pushes outward, releasing energy that keeps the sun from collapsing. These two forces, the inward pull of gravity and the outward push of fusion, are locked in a perfect balance. The sun shines steadily because these forces agree. If fusion ever stopped, gravity would win instantly, and the sun would collapse in a dramatic, catastrophic event. Every second, the sun converts about 600 million tons of hydrogen into helium. Inside the sun's core, hydrogen atoms are squeezed with such force that they merge into helium, releasing an incredible amount of energy. It's almost like the sun is burning its own body as fuel, but instead of flames, the fire is fusion, a process that transforms matter into light. This endless merging is the reason the sun glows with such steady brilliance. Each second, unimaginable quantities of hydrogen vanish forever, becoming the warmth that touches your skin, the light that grows plants, and the energy that makes life on Earth possible. It's a quiet sacrifice happening continuously, far beyond our sight. This fusion process releases neutrinos, ghost-like particles that pass through you by the trillions every second. Neutrinos are incredibly strange. They are so small, so fast, and so uninterested in interacting with matter that they pass through entire planets like arrows traveling through fog. Right now, billions of these particles born in the sun's core are moving through your body without leaving a trace. They don't crash into your cells, they don't slow down, they simply slip through, carrying silent messages from deep inside the sun. Scientists call them ghost particles because they behave like visitors from another world, unnoticed and unstoppable. These neutrinos barely interact with anything, and almost all of them pass straight through Earth. Imagine an entire planet made of solid steel. Neutrinos would pass through it as though it were nothing more than a cloud. They move through Earth in straight lines, unaffected by rock, metal, or water. Even though trillions of them strike your body every second, almost none ever touch a single atom inside you. They simply continue on their endless journey, leaving no footprint behind. It's as if the sun is whispering through the universe, sending signals that almost nothing can hear. Sunlight we see from the sun contains colors that we can't even detect with our eyes. We think of sunlight as warm and simple, but hidden within that glow is a vast rainbow our eyes cannot perceive. Ultraviolet rays, powerful and invisible, stream toward Earth every moment, shaping our climate and our health. Infrared light, gentle and warm, slides across your skin like heat carried by invisible waves. The sun sends out an ocean of wavelengths, many of which we will never see without scientific instruments. Sunlight is far more complex, rich, and layered than our senses can ever reveal. Sunlight that reaches us today began its journey inside the sun tens of thousands of years ago. The light touching your hand right now is ancient. It came from deep in the sun's core, where it spent thousands of years being pushed, scattered, and delayed by dense layers of plasma. Only once it escaped the surface did it sprint through space at the speed of light. In a way, when you look at sunlight, you are looking at a message from the sun's distant past, something that began long before humans kept records or built cities. The solar wind carries the sun's magnetic field through the entire solar system. Every moment, tiny particles called ions stream away from the sun, carrying its magnetic fingerprint across billions of miles. This magnetic field shapes the behavior of planets, comets, and even the boundary between our solar system and interstellar space. It influences auroras, protects us from cosmic radiation, and forms a moving, ever-changing bubble around everything we know. It's like the sun is reaching out with invisible hands, touching every corner of its kingdom. Radiation from the sun has enough pressure to push objects in space. Even though sunlight feels gentle on your skin, it exerts a real force, so gentle on Earth that we don't notice it, but strong enough in space to move dust, push spacecraft, and even sculpt the tails of comets. Solar sails, futuristic spacecraft that travel using only sunlight, work by catching this radiation pressure like a sail catches wind. It means the sun isn't just glowing, it is pushing, guiding, and shaping things far beyond its surface. Over time, the sun loses about 1.5 trillion tons of mass every year through radiation alone. Even though the sun looks eternal, it is always giving itself away. Every beam of light, every particle, every spark of energy steals a tiny bit of its mass forever. This loss is invisible to us because the sun is so huge, but over billions of years, it adds up. The sun is slowly, quietly shrinking as it illuminates the solar system, giving parts of itself away with every passing heartbeat of light. Photons created in the sun's core begin as powerful gamma rays, but stretch into visible light as they escape. At the sun's heart, photons are born as fierce bursts of gamma radiation, so energetic that they could tear atoms apart. But as they struggle through the sun's thick layers, they lose energy, scatter, and shift downward through the spectrum, turning from gamma rays into X-rays, then ultraviolet, and eventually into the familiar visible light we see. It's like every photon takes a long, exhausting journey, calming itself before finally stepping into space as a gentle ray that warms our planet. Sunlight that reaches Earth is at least 30,000 years old. Every ray of light carries a history longer than all of human civilization. It began in a violent fusion reaction deep inside the sun, wandered through the star's glowing interior for thousands of years, escaped into the void, and finally arrived on Earth to brighten your day. Sunlight is ancient, patient, and deeply woven into the long story of the universe, a soft reminder that even the light around us has lived a journey of its own. Sunstorms create storms that can last for weeks. These storms aren't like weather on Earth. They form when magnetic fields twist and release energy, stirring the sun's surface into chaotic patterns that can last for long stretches of time. Some regions, called coronal holes, remain open for months. These areas release fast streams of solar wind that rush past Earth, sometimes creating auroras or disturbances in the magnetic field. They are like open windows in the sun's atmosphere. The sun's gravity is 28 times stronger than Earth's. If you could stand on the sun, which you cannot, you would weigh 28 times more than you do here. But instead of crushing you, the sun's gravity is busy holding planets, comets, and asteroids in their orbits.
The sun bends space and time. Einstein predicted that massive objects distort the fabric of reality, and during a solar eclipse, scientists observed starlight bending around the sun, proving general relativity. A solar storm shut down Canada's power grid in 1989. In a matter of seconds, solar energy surged through Earth's magnetic field, overwhelming the system and plunging millions into darkness. It's a reminder of how deeply connected we are to our star. The sun goes through quiet periods with almost no sunspots. These calm phases can last for years. When they do, Earth sometimes experiences cooler temperatures and subtle changes in climate. One such period, the Maunder Minimum, caused a mini ice age. During the 1600s, Europe experienced extremely cold winters, frozen rivers, and reduced growing seasons, partly due to unusually low solar activity. The sun has siblings, stars born from the same cloud of gas and dust. Long before the Earth existed, the sun was born inside a giant stellar nursery, a cloud so massive it gave birth to many stars at once. These stars drifted apart over billions of years, pushed by gravity and galactic motion. Somewhere in the galaxy, those siblings still shine. Some scientists believe one of them may even have planets, perhaps with life looking up at their own sky, wondering about their cosmic family. It's strange to imagine that our sun, which feels so lonely in space, once had a crowded childhood. One of the sun's long-lost siblings may even host planets with life. Scientists have identified a few stars with chemical fingerprints almost identical to the sun's, the stellar equivalent of family DNA. If any of these stars have planets in the right conditions, life may have formed under a sky lit by sunlight from the same ancient cloud that created us. In a way, life on Earth may have distant cousins shaped by a star related to our own. The sun occasionally unleashes enormous plasma ropes called solar filaments. These filaments are gigantic structures, long, twisting strands of hot plasma held up by magnetic fields. Some stretch across distances larger than the Earth-Moon separation. When they twist too far, they snap and erupt into space as bright, swirling storms.
Watching a filament collapse is like seeing a fiery ribbon fall from the sky, carrying the sun's energy outward into the solar system. Some solar filaments grow longer than the distance between Earth and the Moon. It seems unbelievable, but these loops of plasma, hotter than fire, brighter than molten metal, can stretch over 250,000 miles. They float above the sun's surface like glowing bridges of magnetism. Yet to the sun, they are just temporary waves in a sea of energy.
A mega solar flare could potentially wipe out many satellites at once. Satellites orbiting Earth are delicate machines. A massive burst of solar radiation could overload their electronics, damage their panels, or knock them offline entirely. It wouldn't harm people on Earth, our atmosphere protects us, but our global systems for communication, GPS, weather tracking, and internet could experience chaos for days or even months. This reminds us that space, despite its silence, is full of invisible hazards. A strong solar storm once shut down parts of the Canadian power grid in 1989. The storm pushed electric currents into the ground, overloading wires until they failed. Millions of people lost power in a matter of seconds. Even though the storm wasn't the most powerful the sun can create, it was enough to show how deeply connected we are to our star. Something happening on the sun 93 million miles away can dim the lights in cities on Earth. There are quiet periods where almost no sunspots appear for years. These solar minimums are calm phases in the sun's activity cycle. The sun looks smooth, peaceful, and nearly spotless. But this calm doesn't last forever. Slowly, the magnetic fields reorganize, building tension beneath the surface until new sunspots burst into view again, marking the beginning of a more active phase. The sun moves through periods of rest and periods of energy, like a star breathing through time. One long quiet period, the Maunder minimum, caused a mini ice age in the 1600s. During this time, almost no sunspots appeared for decades. Winters grew colder across Europe and North America. Rivers froze, crops struggled, and the climate shifted noticeably. Scientists still debate exactly how the sun influenced these changes, but it reminds us that even small variations in solar activity can ripple through Earth's environment. The sun shapes the behavior of every atom and molecule on Earth, and even in your own body. The warmth that keeps oceans liquid, the light that helps plants grow, the energy that powers your cells, all of it traces back to the sun. Every breath of air, every drop of water, every bite of food contains sunlight transformed by life into something we can use. Without the sun's steady glow, Earth would be a frozen, silent world drifting through darkness. The sun is the reason we exist. Every atom in your body has been shaped, warmed, or nourished by its light. From the calcium in your bones to the oxygen in your lungs, the sun's energy has touched everything. You are, in a very real way, made of sunlight transformed into life. Every heartbeat, every memory, every dream is powered by a star burning in the quiet distance. The sun doesn't just light our world, it writes the story of who we are. And as we drift gently out of tonight's journey through the sun's hidden stories, just stay in this quiet feeling with me for a moment. If you're somehow still awake and your eyes haven't fully surrendered to sleep, I'd love for you to become a deeper part of this calm little universe we're building here together. If this story comforted you tonight, you can gently tap the like button. It tells the algorithm that you enjoy these slow, soothing science journeys and helps this peaceful corner reach others who might need it too. And if you want more bedtime science stories, more sun, more stars, more impossible cosmic wonders told softly, you can press subscribe so you never miss the next night's adventure. If you're awake enough,
I'd truly love to hear from you in the comments. Where in the world are you listening from, and what time is it for you right now? Seeing those messages from every corner of Earth makes this community feel like one big shared night sky. And if there's someone in your life who might need a calmer evening or a little science to help them sleep, you can share this video with them. Sometimes a quiet story is exactly what someone needs. If you want to keep drifting without waking up, you can explore the Bedtime Science Talk playlist, filled with more soft cosmic journeys designed to gently guide your mind into dreaming. But if your eyelids are heavy now, if the quiet is wrapping around you, you don't have to do anything at all. Just let sleep arrive naturally, softly, slowly. Thank you for spending this time with me tonight. Thank you for being part of this peaceful, curious family. And whenever you want to wander through the universe again, I'll be right here waiting. Good night, dreamer. Sleep deeply.